Continuing in Chapter 2, Section 5, we're going to look more specifically at some of the common functions. What makes them look the way they do? In a previous lesson, when we looked at even and odd functions, we did look specifically at the quadratic and the cubic. So for our attention for this continuation of the video, I'll just remind you that we did look at those in a previous lesson, and so we won't spend the time on those here. We'll look at some of the other common functions and why they look the way they do. So let's look at f of x equals x, also known as the identity function. Okay, we know the domain and range from a worksheet that we did previous. Okay, we didn't talk about increasing, decreasing. We didn't talk about the intercepts. We didn't talk about max and mins. We did talk about the symmetry. I think before we fill in the remaining information here, let's come over here and see why the identity function looks the way it does. So we're going to go ahead and create a t-chart. So the equation is y equals x. Okay, the independent column is going to be labeled with x, and my dependent column is going to be labeled with the y coordinates. Here we just kind of selected, we're at liberty to choose the x's that we want to be parts of this graph. So kind of common practice, we choose these 5 integers. Kind of gives us some negatives and some positives. We take turns putting each of these x's into the equation, which is right here. Well, when you put in -2, your y is also -2. That's why it's called the identity function. Let's take the time to come over here and plot these points. And based on these points, if we have enough points, continue the graph, draw the graph. So I've got -2, -2, -1, -1. I've got the origin, got the ordered pair over 1, up 1, and over 2, up 2. So I can kind of see the pattern of what's happening. Go ahead and connect, trying to draw as carefully as you can, and extend off the grid. This is what we call the identity function. All right, what's the domain? Well, it's all real numbers, my infinities. Range is also real numbers. We did talk about the symmetry. It has origin symmetry. And the name for that is that it's an odd function. Let's go back and revisit these topics as well. Okay, so what's the x interval on which this graph is increasing? Does this graph ever increase? Well, when we look from left to right, and this graph is actually increasing everywhere across its whole domain. So this graph is always going up. It never comes back down, and it never is constant. So what are the intervals of x's on which this graph is increasing? Well, it's all real numbers. From small x to big X, it's always increasing. Does this graph ever decrease? No. So there's none. No decreasing intervals. Does this graph have any x-intercepts? So I look along the x-axis. Yes, it does. We name it with ordered pairs. 0, 0. Does this graph ever cut through the y-axis? Yes, it does. At the origin, that's 0, 0. Does this graph have any relative mins or maxes? Well, that would suggest the graph has to come back down or have some kind of turning point. So no. No maxes, relative maxes, or minimums. Just a reminder down here, I meant to do the same. Origin symmetry. Remember, if a point called xy, having coordinates xy, is on a graph of an odd function, then that means another point that's on the same graph would have to have both opposite coordinates. All right, let's look at number 2 and where the absolute value graph is coming from and why it does what it does. So we're going to create a t-chart. So we've got y equals absolute value of x over here. All right, my t-chart. I've got the inputs and the outputs. Same integers. So one at a time, take each of these x values to populate the y column by plugging them into the absolute value of x. This means what's the absolute value of -2? Absolute value defines a number's distance. Distance is always positive. So if I replace any negative number in here and I perform the operation, I get a positive. This is +1. If I put 0 in, the absolute value is still 0. Well, what if 1 is already positive? Well, then the absolute value bars are Not even, you know, it doesn't have an effect on anything. My answer is still positive, doesn't turn it negative. So notice all your y values are positive. So that means your graph's only going to be contained in quadrants 1 and 2 where the y coordinates are positive. I have no negative y, so I'm not going to be down here in quadrant 3 or 4. So just plotting each of these 5 ordered pairs. And the suggestion is that the graph would continue off the grid this way and this way. So it's like taking a linear function, and any part that's negative down here would have to be reflected upward to be made positive. So let's go over here and fill out this information. We've already done the domain. It's all real numbers. And the range is 0 to infinity. I'm going to come down here. We did talk about the fact that it was even, which even means y-axis symmetry. And when we look at numerically the ordered pairs, if we have a point x, y on a graph of an even function, then that means that the x's are opposite coordinates, but the y's are the same. So I only changed the sign of the first coordinate, the x here. All right, increasing interval. Yeah, I can see that the graph is increasing here. Okay, does the graph ever decrease? It sure does. It's going to decrease and fall here. So what are the intervals of x on which that's occurring? Well, for this graph to be increasing, okay, we're going to start at 0 and we're going to go off to infinity because it never turns back around as suggested by the graph. So parenthesis here. Now remember, for increasing and decreasing intervals, never brackets, only parentheses. On what x intervals does the graph of the absolute value decrease? Coming from negative infinity up to 0. We have an x-intercept and we have a y-intercept. Does the graph of the absolute value function have any relative maximums? Well, I don't see any turning points, you know, where the graph is going from up to down, so I would say none here. But I do have an I do have a relative minimum. There is a low spot in this neighborhood. That graph bottoms out at the origin. So that is, and even though it's not rounded, it's a sharp turn, that's okay. It's still a low spot. So what's the ordered pair? Well, it's 0, 0. I'm going to let you guys fill in number 3. We've done this in a previous lesson. I would do a t-chart right here for y equals x squared. I'd choose the same x values. I'd get the output values, and then I'd put y equals x squared in here, and then I'd fill in all this information. Okay, let's go on to number 4, the square root of x. So I think I'll do the t-chart first over here. Right, now this one's interesting because we don't want a negative number underneath an even root. And this is a square root, that's 2. So you don't want any negative numbers. So if I'm going to choose the negatives that I've done in the previous t-charts, then I'm going to get imaginary numbers, and that's not what I want. So I have to be a little more selective about the x's. So what's the smallest x value that I can take the square root of and get a real number? Well, I'm going to start with 0 in this t-chart. All right, and then I'm going to choose 1 because I can take the square root of 1, and that's a nice number. If I put 2 here, the square root of 2 would have to be found on the calculator as a decimal, so I could plot it. I'm going to see if I can avoid that. What about if x is 3? Same situation. What about if x is 4? Well, the square root of 4 is 2, so I think I'll use that as one of my x's. This is the first time that we've encountered a situation where I have to really be thoughtful about the input values. What's the next perfect square that I could put underneath the square root and get a nice number out of, just to help me plot? Well, that would be 9. So let's go back and find the outputs. The square root of 0 is 0. Square root of 1 is 1, square root of 4 is 2, and square root of 9 is 3. The next perfect square would be 16, but my grid is already going to struggle trying to accommodate my x-coordinate of 9. So 4 points is okay, as long as we get enough points that suggest what the graph looks like and we can complete the graph. We don't always have to have 5. So 0, 0, 1, 1, 1, 2, 3, 4, 2. We can see that it's not linear. It's going to have some kind of bend to it. Now 9 is a 7. 8, 9 would be here. I'd have to go up 3. It's kind of into my T-chart here. That's the best I can do. I'm going to kind of connect these points and suggest the graph continues offward. I can continue putting all kinds of x values in here. All right, the square root graph. Domain, well, the graph doesn't begin until x is 0. And I can go off to infinity. Parentheses, I do include for domain and range, I can use the bracket. The range is 0 to infinity. So this graph is always increasing. This graph will never fall back down. It just keeps getting larger and larger, the y values do. So what are the intervals of x on which this graph is increasing? Well, it's 0 to infinity. But remember, only parentheses. Never decreases. Has an x and a y intercept. This graph does not have a maximum because it doesn't peak anywhere. However, it does have a minimum. The lowest y value is going to be right here. That's the bottom. So we say the relative minimum is at the ordered pair 0, 0, and there is no maximum. Symmetry, none. There's no y-axis symmetry or no origin symmetry. Okay, number 5, I'm going to skip that one as well, just for the same reason that I skipped number 3, because we have already graphed this in a previous lesson when we were talking about even and odd functions. I think that was in 2.2. So, but if I were you, I'd put the T-chart over here and then fill this information and complete this one right here. Let's look at 6. This is read as y equals the cubed root of x. Now, I am going to return, unlike y equals square root of x, I am going to return to using negative numbers. But I want nice numbers to be the results of my input x values. I can take an odd root of a negative number and not get an imaginary solution. For example, let me go to the calculator. I'm just going to choose negative 8. See if I can remember how to do this on this calculator. I want to take the cube root of negative 8. I know that's a weird x, but you'll see in a minute why I'm choosing that. So if I want to take the cube root of negative 8, I believe the first key I need is the variable root. So let's look above this little caret. I'm going to take the cube root. So that's 3 first, right? And then second, and then the little caret key here. So, and then I want to put negative 8 underneath. So this is saying the cube root of negative 8. If it was the 4th root, I'd put a 4 here, and then the same keystrokes. My answer is negative 2. I'm thinking, okay, does that make sense? Is negative 2 times negative 2 times negative 2 going to produce a negative 8? Yeah, it does. Notice there's no imaginary there. Now think about doing the square root of negative 8, which would just be above the x squared key, second x squared square root of negative 8. What does it tell us? Error, because that's going to give us an imaginary solution. Again, cube root, I'm doing the cube root, so I hit the 3 first, second, this little up arrow, caret key, negative 8, enter, and I do get negative 2. So I'm going to do negative 8, I know that's negative 2. Then I'm going to take the cube root of negative 1, that would be the next number that would give us a nice output. And then I'm going to take the cube root of 0, and then I'm going to use the positive 1 and the positive 8. So cube root of negative 1, 0, 1, and 2. And of course, we have our little calculator there to assist. All right, let's plot these. So that's 7, that's 8, negative 2 is here. Negative 1, 0, 0, 1, 1, and then 8, 2. So that graph is slowly, and then it gets kind of steep here, and then slowly leaves the screen here, putting arrows on the ends of our graphs. is called the cubed root. We saw its domain and range earlier. Pardon me, that's all real numbers. This graph is actually increasing everywhere. It never goes back down. X and Y intercept the same. None, no maximum, and no minimum. Because the graph just continues. Symmetry. Yep. Origin. Meaning it's an odd function. And as a reminder, if the ordered pair xy is on the graph of an odd function, then we have to take the opposite of both those coordinates. All right, okay. Now putting it all together. Says graph the common function in a dashed line and the transformation in a solid line. So our first problem is f of x equals the absolute value of x minus 2. We have to identify the common function. So let's just name it. And right here, I'm just going to put the name of the parent function, f of x equals, not to confuse that f of x with that f of x, but just kind of for myself, putting that visual down here. So what's the transformation? This is going to be down 2. And then if you want to think about what characteristics changed once we see the graph on here, that'd be a good thing to kind of think through in your brain, like what changes made to domain, range, mins, maxes, and all of those things. All right, it wants the common function in a dashed line. Okay, easy enough, common function in a dashed line. So that would look something like this. Okay, now then they want the transformation in a solid line. Okay, so what am I doing? I'm shifting every point down 2. So for me, I just choose a few key points. Like to me, this origin is probably a pretty important point. Shift it down 2, so it's going to come down here to 0, -2. This point right here at -1, 1 would shift down to -1, -1, and 1, 1 would shift down 2 units to right here. So carefully, this is a rigid transformation, meaning the shape of the graph doesn't change. All right, and just kind of talking through what are some characteristics that changed. Well, the domain is still the same. However, now the range isn't going to start and go from 0 to infinity. The range of this new graph is going to go from -2 to positive infinity, which means the minimum has changed to 0, -2. The y-intercept has changed. Looks like my x-intercepts have changed too. So a lot of different changes because of the shift down 2. So you can consult the key. I have all the changes listed there, but just kind of wanted to do an overview with you on the video. Let's move on to number 2. All right, what's the parent function? Well, I don't see absolute value bars. I don't see a radical, but I see an exponent of 2. This must be the quadratic. Let's see if I can spell that right. And the equation of the quadratic is f of x equals x squared. Not to confuse that f of x with that f of x, because it's different. All right, the -2 is with the x, so this is going to be a horizontal shift. It's either left or right, and it's going to be right 2. All right, I remember from the ordered pairs, the t-chart, what the y equals x squared graph looks like. So you might want to go back and pull some of those ordered pairs from the t-chart if you've forgotten. It's important to get the parent functions down there correctly, because then if that's not correct, then your transformation is not going to be correct. Yep, and I was supposed to dash that, so let me go back and fix that. I'm going to move every point right to. I think a good point to move right to would be the origin. So now the graph is going to start here. I might choose these 2 points and one at a time shift them right to. So this ordered pair will go right here now, and this ordered pair will end up right here to be symmetric with this turning point. And this is going to be solid. Might move this one to here. Just give me a few more to kind of grab a hold of. There we go. All right, did the domain change? Nope. The range, nope, the range didn't change just by shifting it left or right. The x-intercept changed. The y-intercept changed. The graph decreases on another set of x's. It increases on a different set of x's. So there were some changes. Is it an even function still? No, because there's not y-axis symmetry. I can't fold along the y-axis and have a mirror image now that I've moved that horizontally. Just to kind of, some things to kind of think through when we think about what effect does transformations have on some of these characteristics. All right, let's look at 3. It's the square root. I see this negative right here is a reflection. And it's about the x-axis. All right, thinking about some of the points that I used to create the square root graph, I know for the parent function first, I had these points right here, 1, 1, and then 4, 2. I'm going to dash that. All right, what's a reflection about the x-axis? Well, the y-coordinates are going to be opposites of what they are on the parent function. So we still have 0, 0 here. This point right here, 1, positive 1, is going to be 1, negative 1. This ordered pair, which is 4, 2, is now 4, negative 2. And I'll connect that with the solid line. So changes, well, not the domain. The domain is still all real numbers, but now the range is going to go from negative infinity up to 0. We don't have a minimum anymore. We actually have a maximum. The graph is now decreasing and not increasing. So there's quite a few changes just by that one transformational change. All right, let's look at number 4. Every time I write it, I kind of remember it. That's why it's like square root, and then this is the parent equation. We have a reflection. The x is negative, so it's a reflection about the y-axis. So a reflection about the y-axis means the x's are opposite, but the y's are the same. So this was 4, 2, so now it's negative 4, positive 2. All right, what characteristics change? Well, notice the domain was 0 to infinity, but on my transform graph, the domain is negative infinity up to 0. The range is still the same. I still have a minimum. I now have decreasing intervals instead of increasing intervals. So just some things to think through. Okay, and you can consult the key because it'll give you more details about that as well. Okay, just a few last problems here. All right, we're asked to state the common function name, got it, and equation, and describe the transformation. Well, I see absolute value. So I stated the common function name and the equation. Well, the equation is going to be f of x equals just the absolute value of x. Or this equation is different than that one, but just to identify it. And the transformation. Well, I see a multiplier of 2, so I know that's a vertical stretch by a factor of 2. I also see a subtraction of 3, not with the x. That's a shift down 3. As always, I encourage you anytime, if you feel like you know where this is going, attempt it on your own and then come back and just watch to see how you did. Identify the 2 as a polynomial function. It's quadratic. So what adjustments have been made to this equation based on these numbers? Well, I see a multiplier. So it's a vertical shrink by a factor of 1/2, and I also see a -3 with the x. So this is going to be a shift to the right 3. I see this is the cubed root of x. I see the negative outside, so that's a reflection about the x. Cube root of x all goes together, and this +3 is with the x, so that's a horizontal shift, and that's going to be to the left 3. So a reflection about the x-axis and a shift left 3. And last 3 examples. Describe the general transformation. Notice that we don't have a specific equation. Like I don't see the absolute value, I don't see the square root, I don't see the cubed root, I don't see the x squared. This is just generic notation, general notation. Doesn't matter. Okay, we just want to describe based on if I inserted one of the specific equations here, what would the transformation be if I added 2? Well, I could have made this the square root of x, but the +2 is not with the x, so that's a shift up 2. Okay, I could replace the generic f notation with absolute value and have absolute value of x minus 1. So this is a shift right 1. And same thing here. I could change the f of x to, I don't know, x squared. That parent equation. So I have a couple things going on here. I have a reflection about the x-axis, and then I have a vertical stretch by a factor of 3. And I'm just going to do the little v here, vertical stretch by a factor of 3. I took care of the negative with the reflection, so I don't need to say a -3 right here. All right. Well, hope this helped get your mind around parent functions and the transformations on those.